Today, I'm super excited to introduce our speaker, Wenbin, an assistant professor here at our department. Wenbin's a theorist. He does all things, cares about all things transient, so things that are super energetic, super fast, and cares about studying the physics of what make those come to life. And so Wenbin has been a professor here for a bit, but he's also been a postdoc at Caltech and also at Princeton for a couple of years. And he got his PhD in UT Austin. So yeah, I'll give it up to Wenbin to talk about the Galactic Center's most unlucky star. But yeah, whenever you're ready.
That's a little better, okay? Okay, so today, today the story is at the galactic centers of other galaxies, not in the Milky Way, okay? We will have our Milky Way as a reference, okay? Compare what's going on in other galaxies and in the Milky Way, okay? So the basic picture that I would like you to have in mind is that there is a star that's orbiting around a black hole, okay? There's a lot of things that will happen to the star, and eventually the star will be eaten up by the black hole, and we'll see how that goes, okay? And feel free to interrupt me along the way, okay? So, okay, doing well, okay? So let's think about the Earth, okay? So we're standing, imagine that you're standing on the North Pole, perhaps not necessarily on the North Pole, but you throw something up, okay? If you're extremely strong, you throw things at 10 kilometers per second, which is unlikely, any of us, okay? You have to have a rocket to do this, okay? Even if you do at 10 kilometers per second, it's gonna go up and it's gonna come back, okay? But if you throw a little bit faster, 11.2 kilometers per second, okay, that can be precisely calculated. You throw hard enough, it's gonna fly all the way to infinity. It's gonna leave the Earth forever, no longer coming back, okay? That's the current Earth. Let's imagine that the Earth shrinks, but of course, Earth is not gonna shrink. It's stable, never gonna happen, okay? Just imagine that the Earth shrinks by a factor of 100 and retain the same mass, okay? The Earth now is 100 times more compact, okay, much smaller. Now, in order to throw something away, in order to launch something in space, basically, you need to accelerate things to much higher speed by a factor of 100, okay? 112 kilometers per second, which is currently unlikely, actually. Any rockets, we don't have any rockets that can do this fast, okay? So we're glad that Earth is like this, so it's easy to launch things into the space, okay? Imagine that you shrink the Earth to a tiny, tiny point, 1 centimeter in size, extremely small, like a rock that you can hold on your hand. That's the Earth. Imagine it retains the same mass. Now, in order to throw something away from the Earth, you need to throw things at the speed of light. Okay? That was imagined, it was in the 70s, 1700s. People were thinking, what if there are some miracle objects? Well, of course, at that time, people didn't know. We didn't even know, this black hole and so on. We didn't even know. But people, it doesn't hurt to think about it. What if there are some compact objects that even light cannot escape? Look, for this one, if you shrink the Earth to even smaller size, then even light cannot escape. So nothing can escape. Okay? That was the concept of black holes. Somehow there is this. I was trying to show that is the speed of light. Okay, speed of light is really fast. We're nowhere close. Our technology is something like 10 kilometers per second. We're like orders of magnitude away from being able to do anything near the speed of light. We're just not an advanced civilization yet. Okay? It may take a very long time. Okay, so just to illustrate what a black hole looks like, if you were to hold an Earth-like black hole, it will be something in your palm. Okay. And the most important thing about a black hole, I hope you can take away if you don't know this, is that it has an event horizon. So the event horizon is, you can imagine, there's nothing there physically. It's just a surface, imaginary surface, okay? And this surface is a one-way gate. You can only go in and nothing can get out. Okay? We consider that as a one-way membrane. Okay? It's called a one-way membrane, okay? So let's compare black holes with other objects. Okay, this is in the modern world, in the 1900s. Modern world, in the language of general relativity, invented by Einstein, and actually developed by many other people, including two having Nobel Prize winners. So the modern understanding of black holes relies on this equation. Although Einstein's equation is much more complicated, with tensors. It is actually 16 equations if you want to do into details. But we're going to write that into a simple kind of a conceptual understanding that gravity, as we understand, right, what is pulling what you throw into space back to Earth is gravity. And in the modern language in general relativity, we think gravity as the space-time curvature. So it's plotted like this. Okay. Roughly speaking, you can imagine the space-time is a fabric. Okay. All things are moving on this fabric, and the fabric is bent if you have some massive object. The sun, although as we know, sun is very massive, but it's not as heavy, as dense enough as black holes. Okay. So the sun only bends the space-time a little bit. Okay, because its density is not high enough. Okay, you need to compress this. If you compress the sun by a factor of in density, compress the sun by a factor in density increased by 1,000,000. Okay, then what will happen is that the space-time will bend more. It's a denser object. You can imagine if you were to throw a rock from here to infinity, it will take you much more effort. Okay, and then the second densest object other than black hole is called neutron stars. We're not going to go into neutron stars, but they're known to be very dense. So they are 10 to the 15 times more dense than water, liquid water, extremely dense. You can imagine it's basically impossible for human beings to launch anything away from neutron star. Our technology is just not there. Okay. And then the even denser case, you get the black holes. So black holes, if you the space-time curves, the curvature of space-time is so steep that it's a vertical basically here. Okay. So that's the threshold, that's event horizon. So anything if it's already vertical, there's nothing that can climb out. Okay, from the event horizon. Okay, that's all we need to know in order to understand this kind of the concept. So it's anything can fall in, but nothing can get out. Okay, everything tends to fall in because of the gravity here. Okay, okay. And one important thing is that this size of this one-way membrane. You can imagine. Right now we're drawing a circle in 3D. It's actually a sphere. Okay. Within the sphere, there's a radius. The radius for a one solar mass object, so one object that's as massive as the sun, is only 3 kilometers. And for the Earth, it will be 1 centimeter, very, very tiny. Okay. And we're talking about supermassive black holes, a very, very massive black hole. So M is actually much larger than M sun. So this event horizon, this one-way membrane is actually appreciable in size. It's not very tiny. So we're going to talk about black holes. There's one slight introduction about what we know in over decades of work. Astronomers have done decades of work to understand black holes. So black holes there are 2 categories of black holes as we know currently. Okay? We may discover more in the future, but right now that's limited by our understanding. Okay? There are these, one class is the stellar mass black holes. So these are made by stellar processes. So massive stars, as they evolve to at the end of their lives, they turn into black holes. These are masses somewhere between 3, maybe there is some gap here. We don't know where exactly the threshold is. Typically, you believe there's no black holes less than 3 solar masses. And there's no known processes that can form black hole like that. Okay. Typically, the black hole known are more than 5 solar masses and all the way to about 100 solar mass. Those are called stellar mass black holes. There are known processes that can create such black holes. Okay. An observational fact is that there are also supermassive black holes. These are very, very massive. Their masses are 10 to the 5, meaning 100,000 solar masses, all the way up to 10 to the 10 solar masses. The supermassive black hole actually they span a wide range. Okay, we have no idea how these are formed, but they just exist as a fact. Okay, they lie at the centers of galaxies. So if you go to nearby galaxies, including the Milky Way and nearby galaxies, if you go to the center, you will see the stellar motion, the stars are orbiting around the black hole, okay? And for that reason, we know that there are black holes over there, okay? It's just that we don't know how these are formed. We know actually how these are formed, but we don't know how these are formed. We also don't know if they are mass. I'm pretty sure like it's continuous distribution, but we don't know. Actually, there's no like observations that it's not this population is not constrained, okay? And theoretically, we don't expect any black holes to be that massive. That would be so massive. It would be like a sizable fraction of the total mass of the galaxy. Okay, how did the black hole eat so much mass? Okay, so from our galaxy evolution point of view, we think that black holes should stop here. Okay, so we're going to talk about supermassive black holes today, and they lie at the center of galaxies. Okay, so very important difference between the center of galaxy and the solar neighborhood is shown over here. Okay, so at the center of our own Milky Way, I'll show you evidence for that, but believe me that there is a supermassive black hole and it's about 4 million solar masses. Astronomers have measured that. Okay. Surrounding this black hole within about 10 light years, a very, very kind of a close vicinity. Light year is very large in our everyday life units, but in like astronomical units, light year is not much. Okay. Within 10 light years, there are 10 to the 7 single stars. Okay. And there are about 1 million binary stars. That's in the neighborhood of the supermassive black hole at our own galactic center. It's a very dense stellar field. Compared to the solar neighborhood, this is the sun, and the nearest stellar system turns out to be a triple system by chance, okay, is 4 light years away. Okay, so in the solar neighborhood, they are basically like it's very empty, very much empty. Whereas in the galactic center, it's so dense. Okay, there are so many stars that are orbiting around the supermassive black hole. You can imagine lots of things can happen, right? Maybe the stars can run into each other, colliding with each other. Maybe some stars may get swallowed by the black hole. Maybe some of them may interact with the black hole, right? Those are the interesting processes that I have been studying in the past few years. Okay, let's dive in to see what will happen. Okay, before that, actually, I want to show you the evidence. Okay, this is extremely important. It was awarded Nobel Prize work showing. This is a movie showing stars motion. These are individual stars, okay? As I was drawing the cartoon picture, individual stars are, you can see that over the, I didn't put in the time, this is over 2 decades, okay? Over 2 decades of time, let's say each year you make an image, and then next year or so, you make an image, and then you can make a movie, okay? The movie shows that there are stars that similarly, if you look very, very carefully, of course, astronomers are very careful to look at the images, examine the images very, very carefully, okay? It seems like there are things that are swinging around and there seems to be a dark object over there, okay? That's the center of gravity of the system, okay? This is in the Max Planck and UC Berkeley Rintar-Genzel group, okay? And at the same time, they're using it. The earlier one was using the ESO, the European Southern Observatory Telescope in Chile, and this one is in Hawaii, okay? Using the different telescopes, you see the same thing, okay? But this is slightly more clear because the orbits are drawn, okay? Because astronomers, they can easily draw these orbits, okay? We can easily figure out. So it seems like all the stars are orbiting around that dark mass, although we don't actually see the dark mass because it's a black, okay? We don't actually see it per se, okay? But it's the center of gravity that all stars are orbiting around, okay? So that establishes it as a black hole, and we can easily measure the mass. So this is a kind of a busy slide here. So we have traced so many orbits. These are just some examples. You can imagine that astronomers can label them 1, 2, 3, 4, and go all the way. Actually, these go all the way to almost 100. Okay? These are just some examples. Okay, S2, S14 are the closest ones, and there are S12 and other ones S1. I actually don't know why that's called S1. Maybe that was the first one, the first one that was discovered. But S2 and S14 ends up being the closest one. Okay, so these are the numbers that astronomers measure. So this one has a pericentre radius, meaning that the closest approach. Okay, how close does it get to the black hole, right? If it gets extremely close, we know that it will enter the event horizon. That would be dangerous. And we want to know what will happen to these stars. First, we actually seen multiple orbits. So these stars are safe, at least temporarily, okay? So the closest approach is 117 AU. So AU is the distance between the Earth and the Sun, okay? It's quite far away, actually, quite a distant away. So we want to compare, we know the mass, okay? So the event horizon, the horizon radius, we know is proportional to the mass. We can easily know the horizon radius is about 10% of an AU. So actually, even this one, the closer one, right, the pericentre radius is substantially far away from the event horizon, almost 1,000 event horizon. Okay. It's very safe, really. This star is never going to fall into the black hole, not anytime soon, at least. Within its current orbit, it's just going to go over and over and over. Okay. And each orbit is something like 10 years. Okay. So just to show you, we see these orbits like very easily, but actually astronomically, like doing these measurements is extremely hard. Okay. So this one tick showing over here is 0.1 arcsecond. So arcsecond is an angular size. It's extremely small. It's like if you go to LA quickly and then you hold a ping pong ball over there, so that size. Okay. Astronomers are so good at measuring the precise locations of these stars and then trace out these orbits. So that's why it took 20 years to do this. Anyway, so these stars, their orbital periods are about 10 years. Okay, these are the two closest stars that we know of. There may be other stars that are even closer, but they are maybe fainter, and we don't see them right now. Okay? We don't know their existence. Hopefully, in the future, maybe in the next decade, when our extreme large telescopes are brought online, we may be able to see closer stars. But currently, this is the limit of our knowledge at our own galactic center. Okay, and today I want to introduce a phenomenon that allows us to actually infer in other galaxies. These are millions of light years away, hundreds of millions of light years, or super far away, distant galaxies. There's no way you can directly see those stars, but there are signals that are emitted from those galaxies that actually suggests something similar is happening in a more extreme case. Okay, so before going that, I want to show you that how stars can get destroyed. There are three kind of types of dangers if you get close to the black hole. Okay. The first one I already mentioned that a star can easily get directly captured. Okay, if you go within the event horizon radius, and that's substantial actually for this a million solar mass. So these are units in a million solar mass. That's typical for the supermassive black holes. It's about a few times our sun. Okay, so this event horizon radius can be a few times the size of the star. Okay, so you can imagine it definitely can fit the star. Okay? The star can actually go into the black hole and get swallowed. Okay, observationally, if you happen, of course, these things are very rare. Happen very rare, very rare. Okay, if you happen to see an event like this, will be you just see the star disappear. Okay, the star initially is bright, it's a bright point source, and it disappears. That's all. No other things happen. Okay. Okay. The next thing is very dramatic. Okay. If the star doesn't go in straight line towards the center. Okay. If it's shot like not directly towards the center, but with some angular momentum, meaning that it has some offset from the center. Well, what happened is that if it enters this so-called the dashed line over here, that's about 20 times the horizon radius. Within that radius, the tidal gravity, okay, which is shown over here, the tidal forces, okay, of the black hole will be strong enough to tear the star apart. Okay, imagine that on Earth, okay, we have tides, right? In San Francisco, if you go to the seashore, you see high tide and low tide. That amount of tide is only about a meter tall, okay, a few feet, up to a few feet tall. Okay, here the tides on the star is so strong. Actually, the tides are as large as the radius of the sun. Okay, so basically the entire star is like the tides are going crazy in that case. So in this limit, the star is completely shredded, actually. So the star initially is a spherical object, and it gets elongated and then gets teared apart. It gets torn apart into a basically spaghetti. Okay, I'll show you a movie how that happens. Actually, I have spent the past 5 to 10 years studying these events. Although this particular talk, we're not going to talk about this kind of event, but I'm super excited about these type of events. Okay, this is a movie. It's a numerical simulation. Right now, you can't really see the black hole. The black hole is black. It's at the center here. Black hole is black. Okay, that little dot is the star. The star is so tiny because you want to see what happened to this. Okay, that's the star. You still see the star? Okay, the star is gonna get going. So that's the star. So that star gets shredded, okay, when it gets sufficiently close to the black hole, and then the gas gets spread out into very large distances. Okay, so this happens over a month's timescale. Okay. If this happens, what will happen is that about half of the star's mass will actually go into the black hole, and half will be ejected. That will go into the interstellar medium. Okay, half of the star's mass will come back and then return to the black hole, and then get eaten up. Okay, and this process will emit X-rays, emit optical emission, and we can see those. Okay, it's very bright. It's very, very different from the case where the star is directly swallowed. In those cases, there's nothing. Like you see a point source, and then suddenly the point source is gone. Nothing else. Okay. In this case, it's electromagnetically bright. We can actually see some information. Okay. So this is the tidal disruption event. Okay. There's a third thing that will happen because I mentioned there are binary stars at the galactic center as well. So binary stars, they're bound by gravity. There's two stars that have gravitational attraction on each other, so they orbit each other. Okay. But then on top of that, if the system gets close to the black hole, there are tidal forces. So the tidal forces can also pull the two stars apart. Okay. So what happened is that this is also a dramatic event, although electromagnetically we don't see this event. Okay, we just see that we just see that the two stars are broken apart. Initially, you have two stars. Okay, when the two stars gets close approach towards the black hole, within this critical radius, okay, which is about 200 times the event horizon radius. Okay? If the two stars gets that close, okay, there's a certain chance the two stars get to sufficient close. Then the two stars will be broken apart. One of the star is going to come back. Okay, that remains bound. Okay, and one of the star gets ejected at very high speed. Okay, that star, I call that one the lucky one. It will escape the system. Actually, it will escape the entire galaxy. It will be free floating in the intergalactic medium. Okay. We actually found, astronomers actually found a few of those stars. Actually, they are extremely fast. They're moving at 1,000 kilometers per second, basically zooming past the entire galaxy. Okay. That one got so close to the black hole, it witnessed kind of the event horizon and so on. It must have been so nice, right? If you were, hold your camera and you shot some movies about the black hole, and then you escaped. Okay. Unfortunately, this bound star will have to remain bound. Okay. And that's today's topic. Actually, this bound star actually does a lot of things subsequently. And we know that one thing we're sure is that this star will eventually be eaten up by the black hole, but we just don't know how. Okay. The detailed process that this particular bound star gets eaten up is quite complicated. Okay. We only know partially the information. Okay, which I will walk through. Okay. So let's go to actual observations. I'm a theorist, so all those are speculation. Imagine those are all, you can think about them while you are writing BART. Suppose you can think about this, okay? But these are the actual observations, okay? So this, I'm going to introduce this XMM Newton telescope. This is ESO, okay? European telescope. So it's a space telescope which sees X-rays. Okay, what happens is that this telescope is doing its ordinary mission. Okay, normally it doesn't look at the entire sky. It only sees a tiny very tiny part of the sky. It's doing this kind of observation. Astronomers like to look at everything. Okay, sometimes there's this bright X-ray source. You want to take a look at this. Sometimes you want to look at that. But in between different observing rounds, the telescope has to slew. Okay, the slews from one place to another place. Okay, so these are the slew tracks. Okay, fortunately, people don't actually close the gate when the telescope is slewing. Okay. Sometimes during one of the slews, some X-rays actually enter the telescope, okay? And you know the coordinate, you know where you're pointing, okay? So you know which direction the X-ray is coming from, okay? And what happened is that during one of the slews, which I don't know which of the slew it was, but astronomers can figure it out, okay? Observers can figure it out. But during one of the slews, during that particular galaxy, that's the one galaxy that's very distant away. Okay, 300 million light years is huge, very distant galaxy. Okay, normally you wouldn't even think what that galaxy is doing. Normally you don't know because there are so many other galaxies. Look, how would you know that galaxy is special? Okay, but anyway, during one of the slews, XMM Newton telescope found that there is an X-ray source that suddenly showed up. Okay, so here's the data. Okay. I'm going to show this kind of data a lot, okay? So this is a time axis. This is in days. I'm going to show this entire evolution in thousands of days, 10 years, okay? But that happened in 2010, okay? July 14th, so 10 days after the national holiday. So that happened, okay? It slewed. So during that slew, it was only a few seconds of exposure because it was very fast passing by that point. Okay, so the flux was not very well measured. You need to stare at the source for a long time to measure it very precisely. It was not. That's the error bar. It's quite a large error bar, but we know it's there. There's an X-ray source. Okay, and another piece of information is astronomers are good at looking at the archive. Okay, so they go back to that position. They found that in 1994. The other all-sky survey that happened to be ROSAT, okay, in the 90s, surveyed the entire sky, and actually at the same position didn't find anything. Okay, and there's an upper limit of the flux, and that upper limit is a factor of 100 lower than that. So definitely something flared up. Right, it was nothing there, and then now it's very bright. Okay, and then of course astronomers know what happens, and then let's actually observe it. Okay, let's go look at it. Okay, so in 2010, and then a few more years, 5 more years, I think this is 2014, people use XMM Newton to look at the source again, okay? Kind of, it has faded, okay, at that time, okay? If you zoom into the light curve, so these kind of observations by XMM, one of them lasted for 3 hours, the other one lasted for 23 hours. You may think, oh, actually, it's only 23 hours. That's, it's very short. But actually, for astronomers, getting 23 hours of XMM Newton time is a huge deal. Okay, it's basically you are using that telescope to stare at one source for a day. Okay, it's extremely expensive to do this. Okay, I don't know how much it costs. You can ask the observers; they know how much this costs. Easily, huge number. Okay. Okay. So anyway, it was nice. We measured the flux decay. Okay, let's keep going. And then what happens is that in 2018, we looked at this again, okay, over time. Now the light curve looks totally different. Okay, it was a big surprise to the observers. Remind you that earlier, in something like a 23-hour period of time, the flux was like basically not evolving during that one observing run. Okay, so now the flux is changing like crazy. We have never seen such things before. This is the first time seeing these so-called eruptions. So let me walk you through it. So imagine during this this is very, very long, okay, easily 40-hour long, okay, observing run. The source suddenly becomes so bright and then dims away, okay, and quiescence, and then flare again. And this occurs periodically, okay. At that time, I was a postdoc. I already heard the story. I couldn't believe my eyes. Okay, what kind of theory this is. So I waited for maybe 2 or 3 years to make a theory, because theorists like to jump onto this and then think about them and make theories about this. Okay. But anyway, so you see that these are periodic, and the period is the recurrence of these flares are about 10 hours. Every 10 hours, there's a flare on that particular time. Okay. So they made an image of this, so you can bin this in time, bin the number of photons that is detected by the telescope in time. You see that it's detected. The source is always detected during this entire observing run, and it gets much brighter during that particular. And this lasts for about 1 hour. During that 1 hour of time, it gets much brighter. Actually, one can show this gets brighter by a factor of almost 100. Okay. At the peak, okay, and then it drops down to the so-called quiescent. So during the quiescent state, it's still detected, and then it gets so much brighter during that 1 hour, and then 9 hours of quiescence. That was the observation, okay, and then that was that time, and of course, observers are super excited. Okay, they publish major papers, and then they kept looking at it. It's so interesting. What happened with it? Okay, so it turns out there are 2 more sessions. Okay, 2 more sessions. And the flares got weaker over time. And also the flare timing is also shifting a little bit. It's not exactly 9 hours. Sometimes it's a little bit longer than 9 hours. Sometimes it's a little bit shorter. So for this case, these 2 peaks are separated by 7.2 hours, so slightly shorter. Okay? And this one is slightly longer, 10 hours. So we call them quasi-periodic. Okay, so it's a quasi, so almost periodic, but not exactly periodic. Okay? It got weaker, and then they kept looking, just trying to find more and see what's going on in this case. But these ones are smooth. Okay? There are no more flares, no more these eruptions, okay, in those observing runs. And later on I think in 2023, this thing is still ongoing. Okay? People are still putting telescopes on and still looking at it. Okay? There's still a little bit ongoing. Okay? So a little bit of a flare going on I think this is 2023. Okay. I'm sure that the observers are still looking at this source, okay? But the theorists, of course, were busy, okay? We're looking at this source, so we have to think about it, what's going on, okay? So before that, I'm going to introduce a few more sources before I actually dive into the theory, okay? So there's another telescope called eROSETA. eROSETA is undergoing an all-sky survey, so surveying the entire sky. You can imagine golden opportunity, right, to find such flaring source. Okay, the good thing is that eROSETA has a very large field of view. So each one image is like 1 degree. You can basically see the entire moon. the earlier surveys, they can only see a tiny patch of the moon. Okay, this one is huge. Okay, what happens is that this surveys the entire sky, it scans the entire sky up and then coming down and then up and then coming down and up and come down. So each point gets multiple exposures in this kind of scanning pattern. Okay, so this is a basically, I think this is a huge revolution. It's 30 times faster than the previous survey that we mentioned before. It's extremely good. Unfortunately, only worked for 2 years, and it has been shut off because this is a German-Russian combined mission. So it was shut down since 2021, I think. 2021 has been shut down. So no more data coming from this. We only had 2 years of data. Okay, that's very unfortunate. Otherwise, we would have found a lot more. So in that 2 years of data, there are 4 events. I'm gonna just show you 2 of them. Okay. So this is one of them. So this is the Eero zeta. So astronomer named them like this. Okay, Eero QP1. Okay. So quiescent, and you see some flare. Okay. So that shows that it is undergoing flaring. And if you follow it up, with the much longer staring, because Eero zeta is gone, it's serving other part of the sky. It's not going to come back and look at this. Okay. If you use let's say this telescope called NICER, it's on the International Space Station. NICER can stare at the source for as long as you want because it's a cheap telescope, much cheaper telescope. Okay. They stare at it for many, many days, basically weeks. Okay. They found lots of flares, and these flares are separated by 18 hours. Okay. That's the host galaxy, and these are the flares. Okay. There's another one that was also found, which has a period of 2 hours. There are the 2 hour ones. Basically, every 2 hours you get a flare. There's 18-hour ones. Okay. We also have a few that are like a day or 2 days. Okay. So these are these flares. Okay. Let's go to theories. I'm a theorist. So theorists like to sit down and then use pencil and paper to calculate it. Okay. So let's see what we can calculate. Actually, it's not me alone. There are lots of theorists actually in the entire world. Okay. So there are 3 camps of theory, okay, and each camp has more than 10 papers. Okay, so there's a huge number of papers. Actually, there are more papers. The number of theories is more than the number of sources we know. Okay, so it's a huge number, huge number of theories. Okay, of course we know that most of them are incorrect. That's okay. It could be mine is incorrect. That's okay. We make progress by learning that why it's incorrect. Okay. So my favorite theory is that there is a star orbiting around a supermassive black hole, and I'll tell you why it's quite convincing. And I think it's a main sequence star, meaning that it's a hydrogen burning star like the sun. Okay, it's a main sequence star, and there are theories that are proposing there is 1 star or 2 star or even more stars. But I think that's more complicated. You're putting so many stars. Yeah, there are also theories looking at other type of stars. Also, there are some theories invoking some intermediate mass black holes. And so on. Okay, I'm going to look at this particular case, which I think is the most convincing one. Okay, so that's the theory. Okay, theory is that there is a star orbiting around a black hole. Let's see how that can match observations. Okay, so the first thing you know from the period, it's recurring every orbit. Okay, you can know the 7 major axis during the ellipse. Okay, so this is a generally elliptical orbit. During the ellipse, you can measure this entire thing is a major axis. The 7 major axis is half of it. Half of it called 7 major axis. You can easily calculate what the 7 major axis is. Put in the orbital period is roughly 10 hours, given that there's a recurrence time, and then put in roughly a rough estimate of the mass. You get something like 1 AU. Okay, so this particular star that's doing this within this model is very, very close. Okay, to the supermassive black hole. Remind you that at our galactic center, okay, remind you that we're talking about 100 AU. Okay, so this is a factor of 100 closer. And this one, if you can convert that into the size of the event horizon, it's about 50 times the event horizon. So this star actually get quite close to the event horizon, only a factor of 50. Okay, and the tidal disruption limit, as I was mentioning, if you go within this radius, the star will be shredded. Okay, this is quite close actually. So it's almost shredded. The star is only a factor of 2 safe. Okay, but we know that the star is not shredded. Look, it's still going. It's ongoing. It's for decades. It's still ongoing. Okay, so just put this orbit in and compare this orbit to the orbits that we know at our own galactic center. Okay, And on galactic center, these stars are quite far away compared to this one. Okay, these ones have pericenter radii almost about 100 AU, whereas this one with the same radial axis about 1 AU. We know that eccentricity is also mild. Okay, meaning that if it is highly eccentric, the pericenter needs to be very close. It will be within the tidal diffraction limit. Okay, so it's a kind of a mildly eccentric, almost circular orbit. Right. So our goal is to figure out how did the star get there. Okay. Seems like there is a star there, and how did it get there? Will these stars get there eventually? We don't know. Okay, so that's kind of the story. Okay. Keep in mind it's a mildly eccentric orbit and it's very close. Okay. So there are many questions. Okay, so you can basically ask all the questions and you can think about them in detail and do calculations. We're only going to talk about 3 of them. Okay. Can that star survive? How long does it survive? It's surviving now, okay, because the flares are still ongoing. Okay, it's temporarily surviving. How long will that survive? How long will that last? Okay, and then what is powering the X-rays that we see? Is eruptive flares. What's going on in there? Okay, and then how did the star get there? Okay, there are many other questions. We're not going to go into the details of other ones. Okay, they are the first one is the lifetime of the system. So if you look at these flares, this is luminosity going up and the luminosity going down, and this is we call this quiescent emission. Okay, during quiescence, it's detected because it's still very bright during quiescence. So this kind of technical here, we're looking at a spectrum. Okay, so how many X-ray photons, the individual X-ray photons that are at higher energy? So this is a KeV, so meaning the energy. So these are the high energy photons and low energy photons. These are our models. The solid lines are our models fit into the data. Okay. Of course, there's the actual model is the dash. This is the underlying. The actual model is the dash line. The fitting is a reasonable fit. Okay. This is the intrinsic, and this is accounting for some propagation effect. Okay. The intrinsically during the quiescent emission, the system is quite bright. Okay. And astronomers can easily figure out because we know the distance. We know how bright it is as seen here. We can figure out what is the luminosity, meaning how much energy is radiated per unit time. Okay, it's very bright. You may not have much understanding of what this is. It's about 10 to the 10 times brighter than the sun. Okay, the solar luminosity. So 10 billion times the solar luminosity. Extremely bright. Okay, and you ask how long can this last? The question, of course, comes down to how much energy does it have in total. Right? If you have the total amount of energy, and then it's going to radiate at this rate, okay, how long will that last? Okay, so we can divide the two and then get the energy. So in order to power this, okay, you need certain amount of mass that's falling onto the black hole. Okay, so because the black hole is eating things. Because we're looking at the quiescent emissions, the quiescent emission is always on. So that's not the eruptions. So the quiescent emission is always on. If you forget about these eruptions, it's just a quiescent emission. So the black hole is eating matter all the time. And at the same time, while the black hole is eating matter, it's emitting X-rays. So the matter actually, when the gas gets sufficiently close to the black hole, it gets heated up because it gets near the speed of light. It's very hot gas. So the hot gas will glow and emit X-rays. Okay, so that's the emission. For that, one can estimate how much mass is being eaten up by the black hole. And this basically comes from this mass will have its energy, meaning it comes from the energy budget, because this mass will produce, each gram of mass will produce certain amount of energy, and that can power the X-rays. Okay, so this amount of mass is being lost from the star. Okay, and then you ask, what is causing the star to lose mass? We know that the star is not being tidally destructive. It's not being shredded. Okay, so it turns out the most promising way for the star to lose mass is that because we know that there's a gas structure near here, and the gas will settle down into a disk. Okay, imagine that you have your disk, okay, like this. It's a gaseous disk. So the star's orbit is generally misaligned with this. So it's actually colliding with the disk all the time. Okay, so whenever the star collides with disk, it experiences a wind. Okay, imagine there's matter ahead of you, so you're running into that matter. Okay, and these velocities are very fast because we're very close to the horizon. So these velocities are about 10% of the speed of light. But the star is moving through dense gas, which is in the form of a disk, at 10% of speed of light. Okay, And for that reason, the star experiences a very strong pressure. Okay, imagine you're racing in your car. There's strong wind pressure running on your face. Okay, that's the same thing happening. Okay, so this pressure is so strong, actually, it will heat up the surface layers of the star. Okay, it's so strong it drives a shock into the star. So I'm like schematically drawing that that particular mass will be heated up. The red part of the star is the schematic. Okay, we'll have numerical simulations of this in detail. So one can do such numerical simulations, having a star run into some gas at 10% of speed of light, and you can measure how much mass will be lost. So for typical like disk mass, according to the mass loss rate that we inferred from the quiescent emission, you can also infer that the star actually indeed will lose mass at that rate. Okay, so for those disk densities and so on. Okay, so from this we infer a lifetime of system. So the star typically they are low mass stars. They're like of order of solar mass or slightly less, maybe half a solar mass ish. These are low mass stars. High mass stars are very big, so they actually don't fit in such an orbit. They get tidally shredded. So these are low mass stars. So you can infer a lifetime. So roughly maybe between 100 to 1,000 years. So the systems that we are seeing flaring right now, in 100 years, maybe even more, maybe a little bit more than that, it will be gone actually. So these systems are fairly recent, okay, in astronomical units. Okay, so we're going to talk about what is powering the X-rays. That's another very interesting thing. Okay, so the star is losing mass. Every orbit is losing a small amount of mass. Okay, and we can actually calculate how much mass is lost because there's a mass loss rate, and then every orbit is about 10 hours or so. You can multiply by the mass loss rate by 10 hours. You know how much mass is lost. That's my delta M star here. That's how much mass is lost per orbit. Okay, and you also ask how much mass is accumulated in the disk. Okay, so that is the time scale for mass to accrete on the black hole. There are theories about this accretion. Okay, one can show that actually, because you can imagine this is you're adding mass to this reservoir, and the reservoir takes some time to deplete. Okay, takes a very long time to deplete. So in the end, you accumulate this amount of mass. So it's actually a lot of mass. Okay, so the amount of mass that's in the disk is much, much larger than the newly added mass every orbit. Okay, so that means it's basically you're dumping like maybe 1 cup of water in the pool. Okay, every time. That's basically what the star is doing. Every time you're dumping a small amount of water, into this big pool. Okay, so what happens that in this limit, we know that the stellar debris. So the star is losing mass, and the star this color-ish. Is showing the debris, meaning the star is losing mass, the shock heated mass. The surface layers are shock heated and the mass is leaving the star. Okay, and the gas will be stretched by the tidal forces of the black hole into this elongated shaped structure. Okay, and that structure has very little mass, delta M star. Okay, very little mass compared to what's in there in the disk. So imagine that we're seeing the disk edge on. Okay, and the star has a lot of mass, and the mass will actually run into the disk. Okay, so because this mass is so much less than what the disk is, so this mass we believe will dissolve into the disk. It's like we're dumping some water into a pool, and the water basically mixed up with the rest of the water in the pool. Okay, so it will quickly join the disk. Okay, and whenever that happens, because initially the star's orbit is misaligned and also it's mildly eccentric. Okay, so initially all the debris gas will have a misaligned orbit and also eccentric orbit, and that will be circularized. Everything when you join the disk, things will be circularized, and that during that process there's free energy. There's basically a gravitational potential energy that will be released. Okay, so we think this energy should be enough to power the eruptions. Every time when the star punches through the disk, there's this ramp pressure, the star is losing mass. So the debris here, it's a small amount of mass, will run into the, of course, this is not considered here. It's just looking at a test particle orbits, okay? But in reality, this thing will dissolve into disk. And then over there will be a shock that will heat up the gas, and that will release free energy in the form of X-rays, okay? So that's how we believe the X-rays are produced, okay? So I have a little bit of time to talk about how the star originates, okay? And we're talking about there was a binary star. That's the most likely story, because otherwise, how do you get the star so close to the black hole? Okay, so what happens now? There was the lucky one that went away. we call them hypervelocity star. They escape the galaxy, okay? But then there's the unlucky bound one. The bound one was deposited in this initially highly eccentric orbit. So one can easily calculate, looking at the mass ratio between the star and then black hole, roughly about a millionth. So you can calculate this eccentricity is 0.99. It's very, very highly eccentric. Okay. When the eccentricity gets close to 1, it's highly eccentric. When the eccentricity is near 0, it's near the circle. Okay. It's a highly eccentric orbit. So this eccentric orbit will subsequently evolve over time, okay? Because the star will it loses mass and forms disk, and it will actually run into the disk. Okay, so it collides with the disk, and there will be drag forces. So every time when you run into the disk, you get slowed down a little bit. Okay, every time when you slow down, okay, that slowdown will actually shrink orbit. It gets closer and closer. So that's kind of the anything that you dissipate energy, you lose energy, right? Anytime you lose energy, you get closer to the black hole. Okay, and as you continue to lose energy, eventually you get eaten up by the black hole. Okay? It seems like there's no way for the star to escape. It just keeps losing energy. Okay? There's no way for the star to gain energy. It doesn't. If it has a rocket and it has a boost, maybe they can get out. But in nature, there is no such thing. Okay? It will keep losing energy. Another thing that will happen is that the gravitational wave emission. So the star is orbiting around the black hole, and these two objects, they send out ripples in the fabric of space-time, and that ripples will carry away energy as well. So that will also shrink orbit. So the gravitational waves will take energy away. That will also shrink orbit. In the end, the star can get very close to the black hole. Okay, and currently it looks like this. So currently the star is colliding with the disk, and then it's losing mass, and the mass lost, which is called debris, is forming this elongated structure. Okay, and the debris will dissolve into the disk. Whenever it dissolves into the disk, that amount of free energy will be emitted into X-rays. And there are many other things we can definitely talk about. We can talk about the stellar orbits, because there are Einstein's general relativity predicts that the star is not undergoing elliptical orbit. Actually, it undergoes this kind of precession. Okay, so realistically, this kind of a typical orbit looks like this. We're seeing an inclined orbit. This is an edge-on view. Okay, one of the cases is the black hole. Black hole not only has a mass, also has a spin. And has a spin rate, can be rotating. Okay, so that for a non-spinning black hole, the orbit will remain in that plane. Okay, so if you look at the plane face on, you're going to see that the orbit actually precesses. Okay. Okay, this kind of precession is predictable from Einstein's general relativity, actually. And the spin doesn't, this is for a rapidly spinning black hole. This is for a non-spinning black hole, okay? These are the coordinates that astronomers like to use. We like to use the kind of horizon, roughly the horizon radius as our units over here, okay? That's what the star is doing, okay? That's the orbits, okay? These kind of precessional effects will affect the location where the debris collides, and then the location where the star collides with the disk, okay? That will shift over time, okay? And those will cause timing signals, okay? The timing of the flares will change over time, okay? And we can test this, okay? What if you get even closer to the black hole? So if you get a closer orbit, so originally I was looking at 100 in this kind of Schwarzschild radius, in this horizon radius units. But if you get closer by a factor of 10, then this precession goes crazy, okay? It's not like your ordinary understanding of elliptical orbit. The earlier case was almost elliptical, but the elliptical orbit is only shifting a little bit every time. Okay, but now if you get closer, some of the stars are closer, like the 2.4-hour orbit. That's much closer. So in those ones, this kind of precession go crazy. Okay, so these are definitely happening in these stars. Okay, and if you have a spinning black hole, this is a non-spinning black hole. Everything will remain in that orbit. For a spinning black hole, then actually there's another precessional torque that will actually cause the orbital plane to precess. The orbital plane will go crazy. Look, that's the orbit. So stars, if the black hole is spinning, the stars are doing that. Okay. And imagine you also have a disk. The star will collide with the disk at all different points. Okay. And that will affect the timing of the X-ray flares. Okay. And those can in principle be observed. Okay. So I'm gonna leave my summary here. Since we're out of time, so I like to study these things whenever they show up. There are new phenomena. When new phenomena show up, I like to jump on them and think about them. I also like to point my students through them. Hopefully, they can look at them, independently okay, try to see what we can do. Well, we can do some calculation to understand. Okay, so we conclude that these are very close. The stars are in very close orbits, and they're mildly eccentric orbits. Okay, and the X-ray emissions are powered by shocks. So the star is losing mass, and the stellar debris is shocking the disk. It's the shocks that are powering the X-ray emission, and the system have a lifetime of about maybe 100 to 1,000 years. Okay, it will be gone. Okay, and then there's timing variation because of the orbital precession. The general relativistic effects will cause the orbit to precess. Okay, and that will show up in X-ray timing. Okay, and we think the star originally come from tidal breakup of a binary system. Okay, that's all. Thank you.